right, here we go. So if you're seeing my screen, you see slide 2 about discrete random variables. Are you seeing my screen?
Yeah, I'm seeing it.
Okay, great. So a common question that instructors will ask you here is like, what is the expected value of X? You know, let's say you roll a die. Die has 6 sides. These are the possible outcomes. Are you familiar with that type of problem?
Yeah, but maybe
Okay.
like 36 options.
Well, that's if you roll 2 dice. Let's just say you want to roll 1 dice. The expected value is X times the probability of X. Okay, so for each of these X values, okay, 1, the probability of rolling a 1 is 1/6, plus the 2, the probability of rolling a 2 is 1/6, plus 3/1/6, these are multiplied, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. Okay, so what this becomes, it ends up becoming 1/6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. It ends up being 3.5.
All right.
And so, like you said, there could be another problem here where they say, okay, let's say you roll 2 dice. Okay, and you're right, there are 36 outcomes. There are everything from 1,1 all the way to 6,6. And they could ask you a lot of questions about this. Okay, so for example, they could ask you, you know, what is the probability that the first number is odd?
So wait, I have a question. Should I write down those notes or this
I'm gonna send this as a PDF at the end, and then also a link to the screen recording.
Perfect.
But I would recommend you take notes, but that's entirely up to you.
All right.
Okay, so the questions here, though, you know, it depends on you know, I don't really know what direction to go other than to just tell you these are the questions that you might see. You know, the probability that the first number is odd is the numbers, the total number that satisfy this over what you told me before, 36, because there's 36 options. Okay, so like 1, 1 is good, 1, 2 is good, and so on. Okay, but there's actually ends up being 18 of these that work out. Okay, and what I don't know is what kind of questions you could be asked when you're doing this. Okay. All right, so I'm just looking through your notes here. Passes or fails, distribution. Okay. Plot of PMX. Okay, so let's do something a little bit more straightforward here. Let's say you flip a coin. Okay, so the X, okay, is, well, in this case we'll call it, we're gonna flip a coin twice, okay, and we want to know the number of heads. Okay, so the sample space of this, these are all the possible outcomes. So it's like you could have heads, 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 tails, tails, heads, and tails, tails. So X is the number of heads. X is the number of heads. So what's possible is you could have 0 heads, 1 head, or 2 heads. So when you look at the sample space over here, do you see that the probability that X equals X, I'm sorry, the probability of X, let's just do it that way, little x. So little x, just to be clear, little x is each of these possible scenarios. Okay, like it could be 0 heads, 1 heads, or 2 heads, and we're trying to figure out how many there are. So 0 heads is this one over here. There's 1 out of 4, or 0.25. Okay, 1 head is either this case or this case, heads, tails, tails, heads. So there's 2 of those out of 4 or 0.5. And then the last one is 1 out of 4, which is 0.25. So this right here is what's called your PMF, your probability mass function. Have you seen that in class?
Yeah.
Okay. Now, sometimes they want you to graph the PMF. They want you to make a graph of the PMF or potentially the PDF, which we'll talk about in a moment. So on your PMF, it's little x, okay, and then there's a value at 0, 1, and 2, and I'll make this this is 0.25, and I'll call this 0.5, so that the probability of x equaling 0 is 0.25. So there's a little, I think they call these like a blade of grass in your class, maybe. The probability of 1 is 0.5, and the probability of 2 is 0.25. And you may be asked to make something like that.
All right.
And please interrupt me with questions. This time is for you. So it's whatever you want to talk about.
So for this graph, it's like the horizontal axis, the axis, right? And for
Yes,
the vertical, it's the y, right?
that's right. And
So-
it's P of X. Yeah, go ahead.
Should like the zeros be like on the zero, like
Sure. You could move that over. Like you could move 0 over. I just was, when I graph it on the y-axis, it doesn't look all that clear.
All right, all right.
Okay, now have you talked about a PDF in class?
Yeah, the density, yeah.
Yeah. So the PDF here, we're gonna we're gonna graph it, but let me go back and grab this table and show you how the PDF is produced for this. Okay, so this is your PMF. Okay, your PDF it looks like the following. It's P of X less than or equal to big X here. So it's like this, like what's the probability that X is less than or equal to 0? In this case, I'm sorry, I've got this wrong. I've got the notation wrong here. It's big X less than or equal to little x. Sorry about that. So it's saying like everything less than or equal to 0. So that it's just that one. It's 0.25. But at 1, it's the previous one plus the current one. So it's 0.25 plus 0.5, which is 0.75. And then at 2, you take the current one plus the previous ones. So 0.25 plus 0.5 plus 0.25 ends up being 1. And at wherever you're like, whenever you're at the end of your PDF has to be 1 at the end. So if we're to graph something like this, okay, you have X, you have the probability that big X is less than or equal to X over here. So I'm just going to do this again: 0, 1, and 2, and then this is 0.25, 0.5, and then 1. I know they're not the right scales, but 0 is there, and then 1 is actually 1 is 0.75. Let me call it 0.75, and then 2 is 1. So see how this one grows? Like eventually it has to get to 1. Is the point? Is the point? Okay, so let me move on to another style of question that you might.
So like if I have like a question in the exam, how can I know that it's like, should I use the BMF or the PDF if it's like discrete or continuous?
Well, so you're given a probability question and there's 2 forks. It's either discrete or it's continuous. And things that are discrete are like PMFs, probability mass functions. These are things like tables. Okay, this is like the binomial distribution, dice, maybe cards, I don't know, marbles, stuff like that.
Fine, yeah.
Continuous, I don't know which continuous distributions you've looked at yet in this class. I mean, there's a lot, but I mean, I gotta look here, see what maybe that was in the other PowerPoint that you sent me. You did send me the other PowerPoint. Okay, let me just download that and look at it real quick. But right from the start, you have to decide, which one you're doing so that so that you've got an idea here. Okay, so yeah, here's an example of a continuous random variable from your other set of notes here. Something like this. So how do you know? Well, you know that E is continuous. There's also some known ones like the uniform distribution, uniform continuous.
Mm-hmm.
There's also the normal distribution. I don't know how much of that you're doing yet.
All of these like comes under the continuous, all right.
Yeah. I could make one up. I could literally say, okay, f of x equals x squared from well, let's go x squared over 3 from like 0 to 1. Like this, I could make one up and it works.
Mm-hmm.
So they can either be given or they're known ones, and there's more. Like this list grows. You'll see that in that next class here. Okay. Okay. I mean, here's the next question or next slide here, and this is going back to discrete. You might be given a table like this. It's really no different than the table I showed you above. It's just another one of these tables. Okay. And they tell you the X values in the first column, and then they tell you the probability of X in the second column. Now, here's some rules that you have to remember. All the probabilities of X, they have to be from 0 to 1. Okay, so no negatives. I think that's usually a quiz question that you'll see. Another rule is that the summation of all your P of X's has to equal 1. So that means that all of these numbers right here
Equals to 1.
They have to add up to 1. Okay, is that all right? Is that kind of clear?
Yeah, that's clear.
No negatives, things like that. So this one obviously works. Okay, like some things that the instructor could ask you to do. They could ask you to graph this. They could ask you to graph the PMF. So I've got some room over here. Again, that's just I'll just do it the way you suggest here. Let's clean this up a little bit here. Let's go like that, make it a little nicer. We'll call that 1. So here's 0, 1, 2, 3, and 4. This is your X. This is your probability of X. Okay, so the first one's 0.6591. Obviously, you just graph where you think that is. 0.29, somewhere in there, 0.4. Okay, there's something like that. And that's no big deal. The one that you're probably going to be asked to graph is the PDF. Okay, so we're gonna have to make the table here. We're gonna have to give you the cumulative. I'm sorry, I think I've been misspeaking. This is the cumulative density function here. This is where you take this number, 0.6591, but then
next one.
in the next one you add it to the previous one.
Yeah.
Okay, so I mean, that's why I get a calculator in this, because you'll have some number of calculations. 0.2916 plus 0.6591. That is 0.9507. And then we're going to add the next one to it, 0.0486. So that's 0.9993. So we're getting really, really close here. And then the next one is 0.9999. Wait, I got a mistake here. 0.04.
The first number's incorrect. Like when you.
Oh,
write-
yeah. That's the issue. Okay. So yeah, the numbers do matter. Let me go correct that. I apologize. 0.6561 2916 9477. And then the truth is these numbers aren't all that important. It's the shape that matters here. 0.9963. And then you should what you should always get at the end is 1.
One, all right.
Okay. And then the key here is that when you graph this thing, like it's gonna go to 1 pretty quickly. Here's 0, 1, 2, 3, and 4. And I think I went up. Like there's 1. So at 0, it's 0.6561. So right there, 1, you're at 0.94, then 0.99999. I mean, basically, see how you get there? Now you don't connect these, but I wanted you to see the shape that you get there. And I should have made that point in this previous one also. You want to keep these as like grass, I think is the word they use in there.
Okay.
And the same thing here, like these are little grass stalks. Okay, so if we go back to the original problem, and again, another question, type of question that you could be asked, that's reasonably asked, is they could say, what is the probability that X is less than 1? Okay, and see how this is a less than? This means that it does not include 1.
1, yeah.
So what's less than 1? Well, just this one. So the answer to this is 0.6591. Whereas the probability that X is less than or equal to 1 is 0.659. Sorry, I keep doing that. It's a 61 plus 0.2916. So you gotta add those together.
All right.
Now, another question I could ask you would be, what's the probability that X is greater than 0? Greater than 0 means
Everything.
everything except that. So there's two options here. You can either add or you can subtract. So what I mean by subtract is, and this is what your instructor wants you to do, is it's 1 minus 0.6561. Okay, or like I mentioned, you can sit there and add all the other ones. And when you do some problems like the binomial distribution, usually it's better to subtract rather than to try and add them all up. But they give you the exact same answer.
All right. But like, when I add like those numbers gonna be like the total is gonna be 1, right?
No, not these on the left, because I didn't add the first one. So
Oh,
greater than 0 means it does, and I'll write this here, does not
doesn't include the 0.
does not include the 0. Yeah.
Yeah, that's clear.
Okay, now here's some trick questions, as we say in English, or I like to call them exceptions. I could ask you, what's the probability that X is greater than -1? And you'll notice that -1 is not on this list, but all of these numbers are greater than -1. So this equals 1. Because this is really asking you like everything bigger than -1. -1, is below 0. So these are all included.
So what if like the question is gonna be like X like greater than 5?
Right, good question. So X greater than 5 is 0, because 5 is down here, and I don't know what's going on down there. I mean, doesn't really matter to me because it's only defined in this region.
Yeah.
Here's another question you could be asked: the probability that X is greater than 1.5. So 1.5 is right in the middle of 1 and 2. So but it's only the ones greater than the 0.0486 plus the 0.0036 plus the 0.0001.
Yeah, that's clear.
Great. Let me check and see if you guys are doing expected value, standard deviation on this. You are. Yeah, we should talk about that. Okay. Let me grab this example. Calculate. So this is from the PowerPoint, and we can either do this example or I can provide another one.
As you want.
Say that one more time.
As you want, like.
Oh, as I want. Okay, let's just do this one because it's right here. So the mean is the expected value of X, or expected value. So the expected value of X is the summation of X times P of X. And the formula looks more complicated than it actually is. You just take each X value and you multiply it by the other one.
Yeah.
0.6561. Oh, we already did this one. Plus 1 times 0.2916 plus 2, 0.0486 plus 3 times 0.0036 plus 4 times 0.0001. Okay, and that's our expected value. Now to do variance, and we actually do need to get this number. So let me actually get this because we'll use it in the next step. So just give me a moment here. I'm going to open up a spreadsheet and calculate it. So I've got it for the next problem, part of the problem. And I'll try to type the numbers correctly. 6561, 0.2916, 486, and 0.0036. Okay. All right, so the expected value is 0.4. So before we can do the variance, we have to do an intermediate calculation to do the variance. And the intermediate calculation is the expected value of X squared. And it's really similar to the previous one. You just square the X value and you multiply by P of X. So instead of 0, it's 0 squared times 0.6561. Instead of 1, you square it 1 squared. It's the X value squared, not the probability. Okay. Plus 2 squared times 0.0486 plus 3 squared 0.0036 plus 4 squared times 0.0001, like that. Okay, so let me get that number for you. And you should try to do this on your own if you have time, either now or later on. You're going to get a calculation like that on the exam, I would think.
Yeah, but I'm working on it now.
All right, so I get 0.52 for that.
Mm-hmm.
Okay, so the variance of X is a formula. It's the expected value of X squared, the thing we just found, minus the expected value of X squared. Okay, so the expected value of X squared is 0.52. We just calculated that, minus the number from the previous part of the problem.
0.4 square.
Yes, and this is always positive. So if you get a negative, you made a mistake and you need to look back and just check. And it's easy to make a mistake because you're multiplying and adding and lots of stuff going on.
Like variance must be positive, right?
Variance must be positive because standard deviation is positive. So it's really important to remember that. So this is what, 0.36.
And the standard deviation is like the square root of the variance, right?
The square root of the variance of X, that's right. So it's the square root of 0.36, which equals 0.6, I guess. Please double check that.
Yeah, that's correct.
Okay. Okay, so another like this is like an old like exam question that I've seen a lot is they'll say a 7-sided die numbered from 0 to 6. Okay, and they want, you know, A is what is the expected value of X, you know, B is the variance of X. Okay, so to do, I'm sorry.
We're gonna like do the same thing that we did before, right?
Exactly, except you have to make the table first. So notice there's no table here. You have to make your X and your P of X table. 0, 1, 2, 3, 4, 5, 6. And this time though, it's 1 out of 7 each time. But yes, now you do the exact same thing you did before.
Yeah.
So there are some formulas for like what this distribution is over here is called is a discrete uniform. And there are some formulas you might know about. Let me see if I can find them real quick. Are you allowed to use a reference sheet for the exam?
Yeah.
Could be helpful. Let me try and find something here that might be helpful. Yeah, so the discrete uniform. Yeah, I'm not finding anything that's, I guess, helpful here. I thought maybe your book has this variance formula. Just trying to do a quick search on this to see if you got, if you get anything that's nice. So the like for discrete uniform. So let me see if I can find this. Okay, in this case. Yeah, let me just jump back to your notes here. So this is a problem that your instructor gave. It's a lot like the one that I just did for you, except they say that it could be any number from 0 to 48.
Mhm.
Okay, so the mean you do the same way. You really need that table, but in this case, your table is really long. It's 0 all the way to 48. Okay, so there is a better way, and that's what I was looking for, is to find out like if they give you discrete discrete formulas. I don't know why I can't find this. Discrete uniform. No, it's because it's not helpful. Just want the okay, so here, let's see if we got this. All right, so here are your formulas. You probably saw these in class. The mean is the first one. It says n minus 1 over 2. So in this case, you actually have 49 numbers. I think your n is 49. Does that sound reasonable to you?
Is what?
Let me check I'm trying to figure out what n is. All these, sorry. Why is it never says, okay. Unless n is the range. Let me,
The number of samples, I believe.
I think so too, but the problem is, like, let's just say I made a really small one. Like I said, it could be 0, 1, 2, or 3.
Like,
The
I remember the professor, like when he solved this problem, he just he just add the 0 to 48 and divided by 2.
right, but the number of the reason that works is because the number of samples is 49, and your mean is 49 minus 1 over 2.
Yeah.
Because, for example, for here, we can see that the mu is actually 1.5. It's right in the middle there. Well, how do we get that? Well, we take 4 samples minus 1 over 2 equals 3 over 2, which is 1.5. So you got to be careful there. That's why they do this. There's always, one more than you think.
Mhm.
So that's why I said n is 49. Your sigma squared, well, it's 49 squared minus 1 over 12. Because you don't want to use this approach that we just did, where you take x and you multiply by p of x. It just takes too much time.
Yeah.
So that's why you need these formulas for the exam. And then if you just want sigma, well, you take the square root of that.
Mhm.
Yeah. Actually, what's interesting is they finally, I found it here. And they give you a formula for n here. So n is your upper, or your max, minus your lower, okay, plus 1. Now the only problem with this formula is that it works really well for integers. Okay, but as soon as your x is not an integer, it could become a problem. Like imagine x was 0.1, 0.2, 0.3, 0.4. Then these formulas don't work as well, because you have to account for that in them.
Mhm.
Like maybe I think sometimes they give you a question like they say the pieces of wood are cut from 101.2, 101.3, 101.4,
Yeah.
and so on. And like now your formulas don't work. Now you're better off, let's just say it's these 5. Now you're better off saying, okay, it's 1/5, 1/5, 1/5, 1/5, 1/5, and doing it this way.
Mhm.
All right. I think it goes to the binomial distribution next. Let's see here. Yep, a Bernoulli trial distribution. PMF. All right, let's go to your organic pollution exercise here. We can talk about this problem. All right, each sample of water has a 10% chance of containing an organic pollutant. Assume that the samples are independent regarding the presence of the pollutant, and then 18 samples are taken. So this is a binomial distribution, and it has a bunch of requirements. One is that there's only 2 outcomes. So in this case, it either contains the pollutant or it does not contain the pollutant.
All right.
Another one is that there's a fixed number of trials.
18.
18, okay. And then there's some others here. I don't remember what they are, but that's kind of the main ones that you're looking for, okay. So the expected value of a binomial distribution is n times p. It's the number of samples times the probability of success. In this case, it's 0.1. Yeah, 1.8.
Mm-hmm.
The expected number of samples that do not contain the pollutant, well, that's the n times 1 minus p, because, or some instructors use q here, n times q, but it's the other possibility. It's 18 times 1 minus 0.1.
equal to 0.9.
0.9, and then it has to add up with the other one to the total. Okay, and then from here, I can ask a lot of different questions. I can ask you the probability that X equals 4. Okay, and then there's a formula for this. So do you have your binomial distribution formula?
Not right now, but
Yeah, let me look it up here, because I always use a calculator, so I got to go look these formulas up. So the formula for this is nx p to the x q to the n minus x. And do you know if you're going to have to do this by hand or if you're going to be allowed to use a calculator?
now we're gonna use the calculator. So
Okay. Do you have a TI 83 or 84?
yeah, I have the 84.
Okay. Let me pull up my calculator so you can see my screen, and I'll show you how to do it this if you don't already know. Go find that there.
It's second first, then why no PDF, I believe, right?
Yes, exactly. So I've got a digital calculator here that you can see. Let me just share my screen. And let's see if I get it. Didn't like that. Okay, let's try one more time. New share. There it is. Okay, so you're seeing my calculator. It's not the 84, but it's the same thing. It's like you said, it's under a second distribution, and it's binom PDF because it's PDF because you're only doing it at one point.
Mhm.
Now, in yours, I think it tells you. Could you tell me what the list says here on yours? I think it asks for like
The first thing is the trials.
the trials. In this case, it's 18 trials. What's the next one that it asks for?
It's a P, the probability.
Probably, so that's 0.1 for us.
And then the X value, which is 4.
4. Okay, and then what's the last one, if anything?
That's it.
That's it. Okay, so when you hit paste, it should paste something similar to mine, and it should give you that number, hopefully.
Yeah. Got like the same answer.
Great. So that's too easy. You're not going to get that on an exam. So let me go back and try to explain what you might see on a test, because that's just way too easy. So the questions they like to ask would say something like at most 3. Let me go back and look at the right wording. At most 3 samples contain the pollutant. So when it says at most, you have to decide, is that X less than 3, or is it X less than or equal to 3?
It was the second one, right?
It is. Okay, perfect. So this time you use binom CDF in your calculator. So you got your,
we use the binom BDF when it's like there is an exact number for X,
yes,
right?
yes. This is a binom PDF. So I think it's the same. It's the same thing. This just 18, 0.1, 3.
So when I'm gonna add the numbers to the CDF, there's ask me for the X value. It's gonna be 3.
It's 3 because the way the CDF works is it gives you 3, and then everything below 3. It's giving you 0, 1, 2, and 3.
No, I see.
It's literally giving you the probability that X equals each of those numbers and adding it up.
I see. So the question is not gonna be it's gonna say at least 3 sample.
What could, yeah, it could say it somehow could say probability at least 5.
So how can I use it with my calculator?
So let's write out what it is. This means the probability that X is greater than or equal to 5. Do you agree with that?
Yeah.
So if you think about all the numbers from 0 to 18, that's 5, 6, 7, and so on up to there, right?
Mhm.
And your calculator can't do that. But what your calculator can do is 0, 1, 2, 3, and 4. So this equals 1 minus the probability that X is less than or equal to 4.
Ah, I see.
Because these two together have to add up to 1. So since they want this, you calculate the one on the left and subtract it from 1.
I see. I see.
But there's a few wrinkles to this, a few little modifications to consider. So, let me get that number, and then we'll work on the next kind of thing. All right, you ready for me to move on to another type of question here?
Yeah, I'm ready.
Okay, so it could say something like this, like greater than 13. Somewhere it'll say this. This means the probability that X is greater than 13. And again, if you go to your kind of your list here, that means, well, it's not 13, it's 14, 15, 16, 17, and 18. That's what this is. Your calculator can't do that, but what your calculator can do is X less than or equal to 13. Because that'll give you the 0 to 12, I'm sorry, to 13, which you want, and then you do a 1 minus it. Okay, so there's 4 possibilities, or a couple possibilities. So like, let's say you want the probability that X is less than N. Okay, so what you actually do in your calculator is binom CDF, okay, of comma, N minus 1. So let's say that's 5, you would put 4 here. If it's the probability that X is less than or equal to N, well, that's the easy one. That's the one that is really nice. It's just N. If you want the probability that X is greater than N, excuse me, like we just did here, it's the binom CDF, sorry, 1 minus, we need to do 1 minus that. Okay, comma, and then at this time it is N, because it wants all the ones bigger than that number, just like we did here at 13. We ended up doing less than or equal to 13. And then the probability that X is greater than or equal to N, okay, it's 1 minus binom CDF, comma, N minus 1. And if you can remember this, you got them all down.
Nice. Yeah.
Okay, so a couple more things with the binomial distribution. The mu is N times P. This is the expected value. The sigma squared is N times P times 1 minus P. That's the variance. And then sigma is the square root of that, N times P times 1 minus P. Okay, let's see what else you got here. Oh, Poisson, you got Poisson distribution. Okay. And thankfully your calculator can do Poisson problems. So do you have these from your notes? Because I got to go look them up.
Yeah.
Let me find them real quick. So, because we might use them here. Okay, so I think maybe the hardest part is, so that the PMF is the probability that X equals X is lambda to the K, and sometimes you use N instead of K, e to the minus lambda over K factorial. And there's this relationship mu is equal to, well, I'm going to write that down here. Mu is equal to 1 over lambda. And then variance, the variance is lambda. This is almost always a test question that they ask this. Like they give you a problem where they tell you that the lambda is 6 and they ask you for the variance, and it's just lambda.
Mm-hmm.
So you should expect that. Wait a second here. No. I'm sorry. They're using the mean. Sorry, they're telling you the mean is lambda. The mean is lambda and the variance is lambda. Sorry about that. That's my mistake. These are the same. Okay, so they have to give you lambda. They have to. Now the difference between a Poisson process and like a uniform, discrete uniform, is that Poisson processes can go on forever. Whereas when we were doing a binomial, you know, it stops. Like it's from 0 to 18. Poissons, they go on forever.
Mm-hmm.
Okay, and that's important because sometimes the questions they ask you, you think you can't do them, but you really have enough information to. Okay, so let's look at this question 29 here. And just a tiny bit of help for this question. This is from slide 29 in your class. Did your instructor tell you that the rate is lambda? Is that how they defined it?
Yeah.
Okay, good. So lambda is 4.6. Okay, now you on your calculator have a Poisson option. It's in the same place as the binomial distribution. You have a Poisson PDF and a Poisson CDF. Does that make sense? You have both of those. That's under distributions.
Yeah.
Okay, so the choice to use these is just like before. When you want the probability that X equals a number, use the PDF. But when you want the probability that X is less than, comma, less than, greater than, less than or equal to, greater than or equal to, you use the CDF. And then it's all about like putting the lambda into the calculation.
Yeah, that's clear.
Great. The last problem here, and this is we should definitely look at this, is what's the mean number of earthquakes in 3 years? The mean number of earthquakes is going to be 3 times 4.6, okay, which is 13.2.
Mm-hmm.
So now, what they will likely do is then say, what's the probability of that you have more than one earthquake in 3 years. So this is the probability that X is greater than 1, but the lambda you use is from this number.
Mm-hmm.
Okay, now let's just say instead of 3, they said every 6 years, you would have to calculate a new lambda. You have to do that every time for these problems.
Yeah.
If it's not per year, you got, or if it's half year, it could be half year, 6 months, then you got to cut it in half. Like, All right, Abood. So my lessons generally go about 50 minutes. We started a little late, so I want to make sure we get the full time in. I'd be happy to help you again with the next chapter if you would like. This is kind of the format that you can expect. I'll send you a PDF of the notes right away, and then the screen recording just takes a little bit of time to process and upload.
Like, I have like only one question. You know, I sent you a question from the old exam and it's like related to this subject. So can you please like explain it to me?
Let me try. In the future, try to send this to me ahead of time, because we could have jumped right into this for sure. So, okay. So here's the thing. This problem is, this is a classic problem. It says, what is the probability that the sample mean is exactly, it doesn't say that, but it says exactly equal to 110. So for a continuous distribution, and that's what this is. This is this is normally distributed. For continuous distribution, the probability that X equals any number exactly is always 0. Okay, and the reason is because you're integrating from, like, let's just say here it's 110. You're integrating from 110 to 110 f of x dx, which I know is this is a normal function, but whenever the bounds are the same, this thing always equals 0. So this is your trick question, if you will. A lot of times they ask it on the quiz. Go ahead.
So the reason why we chose 0, because it said it's equal to 110, right?
Yes.
What about like if it said like at least or like more?
Then it's totally different. Okay, then if it's greater than or less than, in either case, you're using a binomial CDF, and I'm sorry, normal CDF. Normal CDF.
I see.
And then you're either you're giving it whatever it needs. It's usually wants mu and sigma and x. Okay, and you might be doing 1 minus it.
I see.
All right, so I really appreciate your scheduling. I'll send you the notes shortly. I got to get ready for my next lesson. If you want to do something else later tonight, I do have some openings. But thank you so much, and I'll see you next time.
Thank you. Thank you.
Have a great night. Bye now.